Let's say I have a little ball, and let's say this little ball is moving round and round in a circle. Now suppose that the center of the circle is here, and I'll draw a line from the center to the ball. Suppose that this distance, this radius, suppose that it is, say, 2 meters. Suppose that that's 2 meters, and the ball, let's say the ball is moving at a certain velocity, and suppose that this velocity is let's say 3 meters per second. So that's our familiar velocity, and we have a distance there to describe the circle. Now we have also seen that the position of the ball can be described by an angle. Let's say I'll call this theta. Now this angle we call it an angular displacement from a reference direction. I can imagine my reference direction to be, for example, that this is the x-axis, so this will be the x direction, and I can think of the center here as the origin. I'll call that O. So theta is the angular displacement, and that describes the position of the ball. Now, but if theta is the angular displacement, now we know for motion along a straight line, we talk about displacement, we talk about velocity. So can we also talk about an angular velocity? An angular velocity. Right, in motion in a straight line, velocity is the displacement divided by the time taken. So for angular velocity, we can imagine that angular velocity is the angular displacement divided by the time taken. Okay. So for example, if the time taken, let's say the time taken to move over this angle is, let's say, 0.3 seconds. Okay. Now, I'm going to just cross that out. Let's say I'll not specify this velocity first. I'll start by describing specifying the angle and the time. So suppose that this angle here is let's say 0.2 of a radian. So in angular displacement in physics, we often use radian instead of degrees as the units for angle. So using this example, let's say this is the time, and that's the angular displacement. We can then find the angular velocity. So the angular velocity in this example is then calculated by dividing the angular displacement of 0.2 radian divided by 0.3 seconds. And then the answer is 2/3. And the units in this case would be radian over second. So radian per second. And we often use the to represent angular velocity. We often use the symbol omega. Now omega looks like W, except that it has rounded bottom. This is the Greek letter omega. Spell it out. It's omega. So that is the angular velocity. Now, having understood what angular velocity is and how we can calculate it, the next thing we need to do is to find out about the relation between the angular velocity, between these 2/3 radian per second, with this velocity v, the number of meters per second that the ball actually moves along the circle. Okay, so this is the if I call this the angular velocity, then to distinguish from the angular velocity, this if you like normal or more commonly used velocity in meters per second, it is usually called the linear velocity. Linear velocity. So linear usually means straight line. Okay, but obviously the ball here is not moving along a straight line; it's moving along a circle. So we still call it linear in the sense that at least over a very short time, maybe 0.01 of a second, it would be moving at roughly a straight line. So we call this the linear velocity, and we want to know how to find this linear velocity, because suppose that I know that the radius of this circle is 2 meters, and I know that the angular velocity is 2/3 of radian per second, then basically I know exactly how this ball moves around the circle. Right, every second it moves over an angle of 2/3 of a radian, and this must mean that the linear velocity, the actual number of meters per second, must be defined, must be fixed by these conditions. It can't just have any value, and that means that in principle, in theory, I should be able to calculate this meters per second if I know that the radius is 2 meters and I know the angular velocity. But how could I actually do that? Okay. So the way to do this is to think about the distance traveled along the arc. So in this time, let's say this time of 0.3 seconds, the ball would have moved from here, from 0 angle to the new position of 0.2 radian. So it would have moved over this arc. Now let's say the value of this arc is S. If I know this length, if I know this arc length, I can find the linear velocity. All I need is to take the arc length and divide it by the time taken. So that's as I normally calculate velocity. Right, the arc length moved over by the ball divided by the time taken. Okay. But how can I find this arc length? Now the arc length is related to the angle and the radius. Let me call this radius r. Now there is actually a formula. That relates arc length to the angle in radians and the radius. And this is actually the definition of the angle in radians. Let me write that down. The definition is like the definition. If I want to find the angle, particular angle in radian, it can be done by taking the arc length and dividing by the radius. Okay. Now, to make sense of this, let's think about what happens when, let's say, when the arc length here, is the whole circumference. Okay, if the arc length is the whole circumference, then the angle would be the whole 360 degrees. All right, but in radians. Now, if that's the whole circumference, for example, the arc length would be 2 pi r, and if this angle goes all the way around, we know that in radians it is 2 pi over radian. Okay, so if you think of this particular example, you see that the formula works, because on the left hand side you have 2 pi, on the right hand side you have 2 pi over r, and r cancels, and that gives you 2 pi. So this formula is the correct formula that relates the arc length to the angle, and this gives us an expression for a formula to find the arc length if we know the radius and the angle, because all I need is to move r over, or multiply both sides by r, and I get r theta equals to s. So now I have a formula for the arc length if I know the angle in radians and I know the radius. So going back to trying to find the velocity, the linear velocity, if we want to think of if you have the angle and the radius, then this arc length would be radius times the angle in radian. It's r theta, substitute it into the s here, divided by the time taken. Okay, so just so it doesn't get too abstract, in this particular example, we know that r is the 2 meters. So let me just remind ourselves that these are actual numbers. So r, for example, r is 2 meters from there. Theta is 0.2 radians from there, and t from there is 0.3 seconds. So these are the examples that we have. But I'm just going to keep the symbols here so that I can get a formula that I can also use for other numbers afterwards. Okay, so this by itself is already a formula that I can use for this particular example. Now, but I also like to write this in terms of the angular velocity, in terms of omega, because that can also be useful if I know the omega instead of the time and a particular time and angle. So, but we know that the angular velocity is theta over t, and notice that I have theta here and t here. So that means that the theta over t here is just the same as omega. So therefore I have r times omega. Omega is theta t. So now I have this formula, v is equal to r omega. Let me write this out. V is equal to r omega. I have a formula that relates the linear velocity to the angular velocity. So that's an important formula, and I'll just work out this, in this case, use this formula to find the linear velocity in this example. I can do that because I know the r, I know that r is 2 meters, and I already have an answer for the omega here, 2/3 radian per second. So if I now try and calculate this, I will take 2 times 2/3 omega, and the answer is 4/3. And since this is linear velocity, the units is meter per second.